So I am using a different camera thing now, so we'll see how this goes. We should be fine, but we'll see. Anyway, so this is video number 3, and now we're going to look at unstable to stable. So what happens for an atom to go from being in an unstable state to a stable state? So we left off by talking about the fact that a nuclei is unstable if the proton and neutron ratio is too large or too small, or if the nuclei itself is too large for the force to hold it together. So anything bigger than bismuth 209, so bismuth with 83 protons. So what we're going to look at now is what happens when we go from an unstable isotope to a stable isotope. So I'm going to start using that word isotope a lot more, because what you find with these much larger elements, these much larger atoms, is that they don't just come in one variety. You will have a multitude of isotopes, and hopefully you remember from Friday's lesson, if you were there. In Friday's lesson, in fact, no, it wasn't Friday's lesson, it was Wednesday's lesson. Wednesday's lesson, we talked about isotopes. So an isotope, just to refresh your memory, same number of protons, but different number of neutrons. So if you want, you can mention the fact that it has the same number of electrons as well, but in the GCSE definition they're not really that bothered about the fact that it's the same protons and electrons. As long as you say that an atom with the same number of protons but a different number of neutrons, that's going to get you 2 marks in the exam, so that's fine. So same number of protons but a different number of neutrons, so that's isotopes. Just a very, very, very quick recap. So a unstable isotope becomes a stable isotope by emitting radiation, and that radiation can come in a number of different forms. There are 3 different forms of radiation that you need to learn, and you need to know a fair bit of detail about each one. Okay, so we've got an example, so let's have a little look. Carbon 14. So carbon, you probably know from the periodic table, is normally 12, so carbon 12. So it has a mass of 12, 6 protons, 6 neutrons, 6 electrons. However, it has 3 commonly used isotopes. So the 3 commonly used isotopes, carbon 12, carbon 13, carbon 14. We're going to look at carbon 14. So carbon 14 still got 6 protons. So hopefully you can do the maths relatively quickly and work out that this has 8 neutrons. Okay, so 6 protons and 8 neutrons. That just happens to be particularly unstable. In the world of carbon, that is very unstable, and that will decay. And when it decays, it actually creates an atom of nitrogen. So it actually creates nitrogen 14. Now, if you look at a periodic table, you should know that you change the element by changing the proton number. And carbon has 6 protons, nitrogen has 7 protons. So we've actually gained a proton. But in the process, we've also lost a neutron, because, again, if you do the maths there, we've gone from a mass of 14, 7 protons, subtract the 2 numbers, 7 neutrons. Oh, running out of space. So something's definitely happened here. Something's gone on. Something has been lost. Something else has been created. We've created a proton, but we've lost a neutron. So something's happened. Okay, so we're going to look at that, the number wise, in more detail in Friday's lesson. This week is just about understanding the three types of radiation, but the radiation comes in different varieties. So this radiation just happens to have been given out as a neutron that's turned into a proton. But again, we will come into that in more detail later on. So an unstable nuclei will become a stable nuclei by emitting radiation. Okay, and like we said, this comes in different varieties, but this whole concept is called radioactivity. The title of this whole unit. So that's radioactivity. So let's have a little look what else. So we've already talked about the fact that this unstableness comes around because of a difference in the proton and neutron number, or if the nucleus becomes too large. But the question is then, like, you know, what determines if something is radioactive? So only unstable elements are radioactive, okay? And they, like we said, they remove that radiation from their nucleus to become stable. So the thing that they give out will be something like an alpha particle or a beta particle or gamma radiation. And they are the three types of radiation that we're going to talk about. And you've probably heard of, I'd say, definitely gamma. It's in popular culture. If you're a fan of Marvel things, and you know it's got something to do with the Incredible Hulk. And alpha particles you should be vaguely aware of because of Rutherford's experiment when he shot the alpha particles at the gold leaf. So beta you might not be as up on, you might not recognize it as much, but that's another type of radiation. So the unstable nuclei want to become stable. So how do they do that? Well, they do it by releasing particles from their nucleus. So how do they become stable? So how do they become stable? So they release particles. The unstable nucleus releases particles to change the proton and neutron ratio. So the unstable nucleus releases particles to change the proton and neutron ratio. This is really important. This has to happen. So they have to change the proton and neutron ratio. Obviously, we know that if there's a big ratio difference, then that's going to have an issue and that's going to make it unstable. So if we try and lessen the difference and we try and make it a much nicer balance between the protons and neutrons, that's when we're going to have a nice stable atom. So there's three types of radiation that you need to know and understand, and I'm going to go through three of them now. So they are called ionizing radiation. So there's three different types of ionizing radiation. And I'm going to summarize them. I'm going to summarize all three of them. And then at the end of this, you guys are going to have a task sheet to fill out that summarizes them all. So I'm going to make some notes. You can either make notes, obviously, as you go along, or you can just wait till the end of the video and then do it. I'll try and take it relatively slowly so you can figure it out as we go through. But obviously, I might be going quicker than I realise because I know what I'm like. I know what you lot are like for telling me that I'm going too fast. So let's have a look. We've got alpha, beta, and gamma. They are our three types of ionizing radiation. So I want to start using my colours now. So alpha. So an alpha particle can also be known as a helium nucleus. Now, if you look at helium on the periodic table, helium has a mass number of 4 and it has a proton number of 2. So a mass number of 4 and a proton number of 2. If you subtract 2 from 4 to work out the number of neutrons, you've got 2 neutrons and 2 protons. So that's what an alpha particle is. An alpha particle consists of 2 protons and 2 neutrons. So when you're describing them, you can literally say one or the other. You can either say it's a helium nucleus, or you could say, oh, it's made of 2 protons and 2 neutrons, but they are the same thing. They are the exact same thing. So an alpha particle is a helium nucleus. Now, it seems a bit odd now, but when we start doing the decay equations, which don't get scared, don't worry, they're nothing awful. My dog's barking in the background, sorry if you can hear that. When we start doing the decay equations, that's when the importance of these numbers, as in the 2 protons and the 2 neutrons, that's when this comes into play. But again, that's Friday's lesson that we're going to look at alpha decay. So don't stress too much, just go with the flow. So an alpha particle is a helium nucleus, so it is made up of 2 protons and 2 neutrons. And again, if you really wanted to draw this, you can do, there you go, 2 protons and 2 neutrons. So that's an alpha particle. So that's our alpha particle. So next up, we've got our beta particle. And a beta particle is literally an electron. More specifically, it's a high-speed electron. It's moving extremely fast. So a beta particle is the exact same as a high-speed electron. And that can be represented as an electron. Literally, that's it. So a beta particle is a high-speed electron. And again, that's it. That's all it is. And then lastly, and I'm not going to use a yellow pen because it inevitably won't show up, alpha, beta, and gamma. So our gamma, not a particle this time actually, but it's a wave. So gamma radiation is emitted as a wave, and it's essentially any leftover energy from the decay. So gamma radiation is emitted as an electromagnetic wave. And you can just literally get away with drawing a wave. Oh, that's a really wonky wave. So yeah, that's literally it. So they are the first things that you need to know about these 3 types of radiation. We have an alpha particle, a beta particle, and a gamma wave. So 2 are particles and 1 is a wave, and it's just leftover energy. I'm just going to write that at the bottom and then actually leftover energy. Okay, so leftover energy. So that is the 3 different types of radiation. Now, it's not just that we need to know. There's actually a little bit more than this. I will go through the next bits. There's about 6 or 7 slides that I've got to go through now, but I'm going to go through each one separately. So I'm going to swap paper and I'm going to talk about alpha first, then beta, and then gamma. And again, this is in the PowerPoint, so what you don't pick up from me, you'll be able to look at in the PowerPoint, and hopefully by watching this and reading the PowerPoint as well, it'll all go hand in hand, and it should make sense. I'm not doing this and thinking, oh, they're never going to be able to work this out. I am thinking, yeah, I've got confidence in you guys, so I'm not stressing. And I'll be online for you to talk to me if you need any help. So alpha particles then, let's have a little look. So there are 3 things that you need to know about each of these particles or wave. you need to know how penetrating it is. So basically, what can it pass through? How ionizing it is. So to what extent does it interact with atoms? So you should remember that an ion is a charged particle. So it's when an atom loses or gains electrons. So radiation does that to atoms. It turns them into ions. So if it's very ionizing, then it will really easily turn an atom into an ion. If it's not very ionizing, then it doesn't turn atoms into ions very easily. And then the last thing you need to know is what it's stopped by. So if you were to put something in its path, what material would you have to put in the way to get it to stop? Okay, so there are 3 different things to know about each one. And we're going to start with alpha radiation, like I said. So alpha particles. Helium nucleus, like we've already said. They have got 2 protons, 2 neutrons. So if we're going to represent an alpha particle, we represent it with an alpha symbol, which is like that. And we represent it with a 4 because it's got a mass of 4. 2 protons, 2 neutrons, that's a mass, that's 4. And we represent a 2 at the bottom. Okay, so it's got 2 protons, got an atomic number of 2, and it's got a mass of 4. So it is basically like a helium nucleus. It's a helium nucleus because it doesn't have any electrons, so it couldn't be an atom because it doesn't have any electrons orbiting the nucleus. It's literally just the nucleus. Okay, so they can't travel particularly fast. All right, this is just a general property of these particles. It can't travel fast because in radiation terms, it's got a very large mass. So because it's got such a big mass, it can't travel particularly fast. So it will, because it doesn't travel very fast and it's just sort of bumbling along, it actually collides with a lot of other atoms. So by colliding with a lot of other atoms, it actually is very ionizing. So alpha radiation is actually very, very dangerous because it can really, really easily destroy your atoms. So it's not very good if you get caught in the path of alpha radiation. So alpha particles, they travel slowly. So they travel slowly because of their large mass. Okay, and then again, 4 doesn't sound very big for a mass, but in terms of alpha particles, it's very, very big. It's the biggest type of radiation. So because they travel slowly, they collide with a lot of atoms, and because they collide with those atoms, they have a great affinity for ionizing. So travel slowly because of their large mass, collide easily with other atoms, so it can easily ionize. So if we were going to put this in terms of a property and we were talking about the ionizing power, you would say that they are highly ionizing. Okay, so they are highly ionizing, and that's really important because it's, again, a common exam question. Put these 3 particles in order in terms of their ionization power. Always alpha first. Okay, which is the most ionizing, alpha, beta, or gamma? Alpha. Okay, so highly ionizing, and again, remember, it's how easily can they pull electrons off the atoms. Okay, so penetration then. So they can't particularly penetrate through a lot. One alpha particle will ionize 10,000 atoms, so it will quite easily just bumble along, collide with 10,000 atoms and remove electrons from all 10,000 of those atoms. But because it's putting so much energy into ionizing those atoms, it really, really quickly runs out of energy itself. So because it runs out of energy so quickly, it can't really penetrate a lot at all. So it's got a very low penetration. So very low penetration due to being highly ionizing. So as bad as alpha radiation is in terms of ionization, actually it barely penetrates anything. So as fast as it starts to ionize, it runs out of energy and it can't really penetrate anything. And then that then leads on to the fact that you can stop alpha radiation with paper. So you can literally hold up a sheet of paper in front of alpha. If something was emitting alpha radiation and you held up a piece of paper in front of it, the piece of paper would stop it. If you didn't have a piece of paper, if someone was holding up some kind of material that was emitting alpha radiation, if you stood like a meter away, it would stop in air anyway, because the alpha particles can't even fight their way through air molecules. So it really, really, really can't travel very far, and it's stopped very easily by paper. So stopped by paper. You can also say it's moves only a few centimeters in air. So basically, if you stood far enough out of the way, then you wouldn't be affected by it. Okay, so that is alpha penetration. I'm going to be really rude and yawn. Oh, excuse me. So that's alpha radiation. Now we're going to look at beta radiation. We're going to look at beta particles. So beta particles. So like we said, it is one single electron. That's it. And what you should remember is that an electron has very, 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 very little mass. Very little mass. We say it's basically zero. We say that the mass is negligible. It's, if you want to be specific, it's 1/2000th of a proton, but that's just ridiculous. So we say it's basically zero. A beta particle is represented as a beta symbol, which is like a B with like a nice long tail. It has zero mass, so we put 0, and it has a charge of -1. So we're going to put a nice little -1 there, just to remind you as well that anything with a charge of -1 is an electron. Okay, they are electrons, but they actually come from the nucleus. So that will sound really, really weird, because you know that electrons aren't in the nucleus, they're on the shells. But again, when we come on to beta decay in a couple of lessons time, you'll understand that something weird and wonderful happens, and we can turn a neutron into an electron. And again, don't stress, don't panic, just take it on board, and we'll do that in a couple of lessons time. So beta particles then, they are basically an electron. So they're really, really small, and they move a lot quicker, so they're less ionizing than alpha particles. So they move faster than an alpha particle, so are less ionizing. Now, they're less ionizing, but I still wouldn't like to get in the way of a beta particle. You know, if there was a beta particles coming at me, then I'd still be interested in getting out of their way in terms of their ionization power. So they're still going to affect your cells. They're still going to affect the atoms that make up your cells and can ionize them. So you don't want to be near it, but it's not as strong as a beta particle. Okay. In terms of their penetration power, they are more penetrating than an alpha particle because it doesn't ionize as well. So because it doesn't ionize as well, it doesn't run out of energy as quickly. So it's more penetrating. So less ionizing, so has more energy because it's not trying to put all its energy into ionizing things. So less ionizing, so has more energy, so is more penetrating. Okay, so it's got more penetration. So like, it sounds really stupid, but when you write in, if you're asked to describe it, you would say medium penetration, because it's not as penetrating as something else, but it's not less penetrating than something else. You just say it's got a medium level of penetration. Beta particles are a little bit tougher than alpha particles. So alpha is going to be stopped by your sheet of paper or stopped by moving through air. Beta particles are a little bit tougher. So beta particles need something a little bit thicker, and they need to be stopped by aluminium. Depending on what beta particle it is and how thick the aluminium is, they'll be stopped by, they could go through aluminium foil, but you'd need like a proper sheet of aluminium. So beta particles are stopped by aluminium. They can pass through paper. There's this really like common exam question which gives you like, it shows you like a box or something, and it says, oh, this corner is made of aluminium, the rest is made of paper. The particles that we fired at it went through the paper but didn't go through the aluminium in the corner. What type of particles are they and why? And then you'd have to describe the fact that they were beta particles because they went through the paper but they were stopped by the aluminium in the corner. And it's just do you know the properties? So by knowing the properties, can you then describe what's going on the page in the question? And I think that's a really nice question. That's like super easy marks. So you'd be silly to miss something out like that. Right. So lastly, we have got our gamma wave, which I'm just going to change the paper for. So gamma wave. Right, and as we said before, they are a electromagnetic wave. This is very basic. Electromagnetic wave. And they have no mass and they have no charge. So they have no mass and they have no charge. So let me think. So you would literally just represent it as a wave like that. No mass, no charge. I just thought of something else that I need to go back and add into the other sheet, so I'll do that in just a minute. So they are the least ionizing gamma waves because they have no mass, they've got no charge, but because they've still got energy, they can still cause ionization. They will still cause ionization, but it's just the least ionizing. So least ionizing radiation, but can still cause it. Okay, so the least ionizing but can still cause it. Okay, in terms of penetration, they are highly penetrating. So gamma is always made out to be the worst. I think in like TV and film and things, they always try and make gamma out to be the worst, but actually gamma's not very ionizing at all. So it's actually not as dangerous as alpha radiation, but they're very penetrating. They are very, very penetrating because it's particularly difficult to stop. So even though they don't ionize as many atoms as alpha, when gamma starts moving, it then becomes very tricky to stop, if that makes sense. So you can stop, I could use this piece of paper to stop alpha particles, but the gamma would just keep going through this until it hit something that would stop it. Okay, so they're the least ionizing radiation, but highly penetrating. So very difficult to stop. Oh, I was doing so well on my notes. Highly difficult to stop. So it would just keep going and keep going and keep going until something was put in the way to stop it. They are stopped by a few centimeters of lead or a few meters of concrete. So lead is a lot more dense than concrete. So to stop it, you need to use a few centimeters of lead or a few meters, and that is right, a few centimeters of lead or a few meters of concrete to stop the gamma. Okay, so just to go back very, very quickly, the thing I forgot about, gamma waves have got no charge, because you can get asked this. I do forget this all the time, so I apologise. Alpha particles have got a charge. They've got 2 protons. Protons are positive, so it has a 2+ charge. So I'll just scribble that in just under here. So it's got a +2 charge. So alpha particles have a +2 charge, and then beta particles are an electron. They are just a 1 high-speed electron, and we've already written in here that they are -1. An electron has a charge of -1, so a beta particle has a charge of -1. Charge of -1, mass of 0. This one, mass of 4, charge of +2. And then a gamma wave, as you can see, you know, there's a distinct difference in the notes, isn't there? Like, there's quite a few notes there. Not an awful lot to say about gamma. They're an electromagnetic wave. They have no mass, no charge, least ionizing, highly penetrating, and you need to use a few centimeters of lead or a few meters of concrete to stop the gamma. And that is it for the 3 types of radiation. So you will find a worksheet on the Google Classroom, and that has basically got these 3 things summarized, so you can use these notes from the video, use the PowerPoint to go back through and make yourself a nice summary sheet, save it, print it out, stick it on your wall, do what you want with it. It's up to you, but that is there for you to summarize all your notes together. So that is your first lesson in stable and unstable nuclei and radiation. I hope that wasn't too scary. On Friday's lesson, we're going to be doing alpha and beta decay. We're going to start, I think I'm going to split it up and do alpha first, and then I think I'll do beta next Wednesday. Only because it gets a little bit tricky. I just want to make sure that we can do this in good detail. I will be on Google Meet, ready to talk to you guys. If you need me, you know the deal. The code is at the top of the classroom. Please don't forget to sign the register, and ask me any questions that you need. Can I just also say that don't just sign the register and then don't submit work. You signing the register isn't you submitting the work. That's why people aren't getting great scores in terms of effort, because some people are submitting the scores and then just not doing any work whatsoever. I need to see the evidence of the work, and don't forget to do the Seneca as well, please. Okay, I'm sorry to be a nag, but I am teaching you a new topic, and it's hard because, you know, it's I'm teaching you from home, and I know you guys are at home, and I miss teaching you in school, but we're just going to have to try and do this the best that we can. So any questions, just let me know. You know where I am. I'll answer whatever you need. Just give me a shout, and I will speak to you in the lesson. So yeah, bye bye for now. Hope this was okay.